Picture this: a world powered by the sun's boundless energy, where clean electricity flows as freely as sunlight itself. Sounds like science fiction? Think again. The future of sustainable power is already here, and it's all thanks to the marvels of solar technology. Welcome to the Clean Energy Journey YouTube channel, where science meets sustainability. We're here to share how green energy will save our planet in the future. And today, we're diving deep into the fascinating physics behind solar energy harvesting. Solar energy isn't just a passing trend, it's absolutely crucial to our global energy transition. As countries worldwide strive to break free from fossil fuels, solar power shines as a beacon of hope. Here's a mind-blowing fact. In just 1 hour, our planet receives more energy from the sun than all of humanity uses in an entire year. Talk about untapped potential. But let's be clear, solar panels aren't magic. They're incredible feats of engineering built on rock-solid scientific principles. We're talking optics, electromagnetism, and even quantum mechanics. In a nutshell, here's how it works. Sunlight carries energy in tiny packets called photons. Solar panels capture these photons and convert them into electric current. That electricity then powers our homes, industries, and cities. Simple, right? Well, not quite. Let's break it down further. To truly understand solar energy, we need to start with the basics of light itself. Light is made up of those photons we mentioned earlier. Each photon carries a specific amount of energy, which is directly related to its frequency. This is why sunlight includes a whole spectrum of wavelengths, from infrared to visible light to ultraviolet. Here's where it gets interesting. Solar cells can't use all of this light equally. Some photons don't have enough energy to excite electrons in the solar cell material. Others have too much energy, and that excess just gets wasted as heat. This is why solar panels are carefully designed to target specific ranges of the spectrum, mainly focusing on visible light. Now, let's dive into the heart of solar energy, the photovoltaic effect. This is the key phenomenon that makes solar cells work. When photons strike a semiconductor material, usually silicon, they can transfer their energy to electrons in that material. This extra energy allows the electrons to break free from their normal positions, creating what we call electron-hole pairs. But freeing up electrons isn't enough on its own. Solar cells are cleverly structured to create an internal electric field. This field acts like a one-way street, directing those freed electrons into an electrical circuit. And there you have it. Photons in, electrons out. Electricity produced. The structure of a solar cell is crucial to its efficiency. On top, you'll find an anti-reflective coating. This isn't just for looks. It ensures that as much light as possible enters the cell instead of bouncing off. Beneath that is the all-important semiconductor layer, where the photovoltaic magic happens. Finally, metal contacts collect and transport the electrons, creating usable current. The efficiency of a solar cell depends on several factors. The purity of the semiconductor is crucial. Fewer defects mean fewer lost electrons. The thickness and design of the layers also play a big role in maximizing photon absorption. And of course, that internal electric field needs to be perfectly aligned to guide those electrons where we want them. Now, let's get quantum. This is where things get really fascinating. Every semiconductor has what we call a band gap energy. This is the minimum amount of energy a photon needs to excite an electron. If a photon doesn't have enough energy, it can't free an electron at all. If it has too much energy, that extra gets lost as heat. This phenomenon, called thermalization loss, is a major reason why we can't convert 100% of solar energy into electricity. In fact, there's a theoretical limit to how efficient a single-layer silicon solar cell can be. It's called the Shock-Liquizer limit, and it caps efficiency at around 33%. This might sound disappointing, but it's actually driving incredible innovation in solar technology. Speaking of challenges, let's look at where solar stands today. Commercial solar panels typically operate at about 20 to 25% efficiency. Impressive, but still far from that theoretical limit. Manufacturing costs have dropped dramatically, but producing high-quality, silicon and advanced panels still requires significant investment. And of course, there's the intermittency issue. Solar power isn't available 24/7, dropping off at night and on cloudy days. But don't worry, the future of solar physics is incredibly bright. Researchers are exploring amazing new materials like perovskites, which offer high efficiency and potentially lower production costs. Multi-junction designs stack multiple layers with different band gaps, allowing panels to capture a broader range of the solar spectrum. This could push efficiency way beyond silicon's limits. Nanotechnology and quantum dots are opening up entirely new possibilities, allowing us to custom design materials at the tiniest scales to enhance photon capture and electron flow. And we're not stopping at silicon. Organic photovoltaics, flexible panels, and hybrid systems are all on the horizon. So, what have we learned? Solar energy harvesting is a perfect example of how abstract physics principles can be transformed into world-changing technology. We've taken our understanding of photons, semiconductors, electron flow, and quantum effects and used it to power millions of homes worldwide. It's a testament to human ingenuity and the power of scientific understanding. As we wrap up, I encourage you to keep learning about renewable energy. Follow the latest developments in solar technology, and think about how science is directly impacting our fight against climate change. The clean energy revolution is happening right now, and you're a part of it. Before you go, I'd love to hear from you. Which solar innovation excites you the most? Perovskites, multi-junction cells, or quantum dots? Let us know in the comments. And don't forget to like, subscribe, and hit that notification bell to stay up to date with all our latest videos on the clean energy journey. Together, we can build a brighter, cleaner future powered by the sun.